A load-bearing member can only offer so much resistance to stress before it reaches the breaking point. The stress on an object that causes it to fail is called the maximum stress. Because the stressed area and the composition of a particular load-bearing member remains constant, how close the stress is to the maximum stress depends solely on the load that creates the stress. The largest load a load-bearing member is allowed to support is called the maximum working load. For the same load, the stress varies inversely with the stressed area. So for the same load, if we decrease the stressed area, we increase the stress. And if we increase the stressed area, we decrease the stress. When engineers design load-bearing members, they have to make the stressed area large enough so the actual stress will never approach the maximum stress when the maximum working load is applied. Let's look at a practical application to see how this is done. We will look at constructing an overpass that will be supported by two identical concrete pillars. The first thing we have to do is determine the maximum working load that will be on the overpass at any given time. This will be the theoretical maximum weight caused by the vehicles plus the weight of the overpass. Let's say for our overpass, the maximum working load will be 1,000 kilonewtons. Next, we determine the maximum stress of the material. We take a sample of the cement that will be used to make the pillars, and we will let it harden in a cylindrical form of known diameter. We calculate the stress circular area of the test specimen using its diameter. So let's say the diameter of our test specimen is 0.254 meters. Using the formula for the area of a circle, we find that the stressed area of our test specimen is 0.0507 meters squared. We then place the hardened concrete test specimen in a hydraulic press and gradually increase the force on the stressed area until the specimen breaks. Let's say our specimen fails when 300 kilonewtons of a force is applied to the stressed area of the specimen. Using the formula stress equals load divided by area, we can say maximum stress of concrete equals the load at which the specimen fails divided by the stressed area of the test specimen. So the maximum stress of concrete will equal 300 kilonewtons divided by 0.0507 meters squared, and the maximum stress of the concrete will equal 5917.2 kilopascals. Since stress equals the load per square meter, the above value for the maximum stress is constant for all stressed areas of that particular concrete. Now that we know the maximum working load of the overpass and the maximum stress of the concrete, we can calculate the stressed area that'll give us the maximum stress when the pillars are subjected to the maximum working load. Since stress equals load divided by area, we can substitute maximum stress of concrete equals maximum working load divided by the stressed area of pillars at maximum stress. Rearranging the preceding formula. Stress area of both pillars at maximum stress equals maximum working load divided by maximum stress. Stressed area of both pillars at maximum stress equals 1,000 kilonewtons divided by 5917.2 kPa. Stressed area of both pillars at maximum stress will equal 0.169 meters squared. Therefore, the stressed area of one pillar is 0.169 meters squared divided by 2, or 0.0845 meters squared, when the maximum working load causes maximum stress. So, if we build the two pillars so their total stressed area was 0.169 meters squared, the pillars would be at maximum stress and ready to fail when subjected to the maximum working load. To keep the overpass from failing when subjected to the maximum working load, we increase the cross-sectional stressed area of the pillars to reduce the stress. The factor by which we increase the pillar stressed area above the value that causes maximum stress at maximum working load is called the factor of safety. Let's have a factor of safety of 10. So we increase the total stressed area of the pillars by 10. So the actual stressed area of the pillars will equal a stressed area of both pillars when maximum working load creates maximum stress multiplied by the factor of safety. So the actual stressed area of both pillars will equal 0.169 meters squared times 10. The actual stressed area of both pillars will be 1.69 meters squared. But the above stressed area is for two pillars. The stressed area for one pillar will equal 1.69 meters squared divided by 2. So the stressed area for one pillar will equal 0.845 meters squared. Let's find the diameter of one pillar with the factor of safety built in. Since the stressed area of one pillar is the area A of the circle having a diameter D, we can use the following formula to find the stressed diameter. A equals 0.7854 times D squared. Rearranging the formula, D squared equals 1.076 meters squared. Taking the square root of both sides, D equals 1.04 meters. So if each pillar had a diameter of 1.04 meters, the maximum working load would produce a stress of 591.7 kPa, or 10 times lower than the maximum stress.